Thank you. So I'll present, thank you everybody for being here. I'll present the work I have done with colleagues, and this work is about formal models for monotonic pipeline architectures. The plan of my presentation will be the following. First, I'll recall the hardware context in which we are working, and then I present a generic architecture model that we have elaborated. I'll discuss about also some of the properties of this on this model, especially, and the properties we are interested in, monotonicity. And then I'll just present some experimentations we are doing now in our laboratory. And the last, I try to draw some conclusions. So first, the context in which we are working is the context of real-time systems. And we are interested in design, validation, and certification. We are mainly, for this talk, we'll be mainly interested by hardware architectures. And what we are looking for is how to make accurate and safe worst case execution time bounds. In fact, this worst case execution time is very complex to compute. So we have to first have architectures that make such analysis that are almost based on WCET, tractable analysis. So the architectures play a role here. And then we have to validate the architectures of the properties of these architectures and the assumptions that we make about these architectures. Here, I recall a well-known textbook pipeline architecture. In this pipeline, we have 4 stages: the fetch stage, the fetch, decode, execute, and commit stages. And what we mean by executing instructions over this pipeline in a pipelined way, at time 0, the pipeline is free. So the first stage is free. So the first instruction can enter the pipeline at time 0, but the instruction 1, 2, 3 cannot enter because the fetch stage is busy. At time 1, the instruction 0 leaves the fetch stage and enters to the decode stage. At that time, since the fetch stage becomes free, instruction 1 can enter to the fetch stage. So this is what we call the pipelined execution of instructions. And we will be interested in our study in more complex architectures, and we will come back to these architectures later. For these architectures, in order to make analysis more tractable, we have a phenomenon that is usually called architecture anomalies, architectures timing anomalies. A timing anomaly occurs when the usual assumptions that to make tractable analysis are broken. So, example of a usual assumption is that if the instruction make a cache hit, then we expect to have a globally faster execution time. And if an instruction makes a cache miss, we expect to have a globally slower execution time. And an anomaly is when we do not have these two like properties that we expected, but we have the inverse. That is, when we have a cache hit, we have a slower execution time, or when you have a cache miss, we have a faster execution time. And if we have these anomalies, then the assumptions that we usually make for computing the complex WCAT are broken, so our calculus of WCAT is not anymore valid. So this work is done within what we call the PROTIP project, and our goal is to elaborate a framework for the development of trustworthy generic hardware architectures. In fact, we are mainly concerned by designing basic components for the proofs of absence of anomaly. We aim also to use the right tool for easy validation, for an easy development based on formal methods. For our study, for the development, we have considered event B. For proofs, we have considered COC, Isabelle, HOL, TLA plus, and event B. For model checking, we consider TLA plus, and for small simulations, we consider COC. Now I present the generic architecture model. For presenting this model, I'll first consider the static architecture model, then the dynamic architecture, and last, I'll present the generic transition system that we have considered. First, about instruction and stages. We consider that instructions are finite and totally ordered. For the stages, we also consider that stages are finite, partially ordered, and well-founded. That is, we cannot have an infinite descending or ascending chain of stages ordered according to the partial order. We model the pipeline as an acyclic state graph, and to each instruction is assigned a path over this graph, and all this path starts with a virtual stage that is usually called pre, and a last virtual stage that is usually called post. With respect to delays, we have two types of delays. The delays that we suppose that for the computation of an instruction when an instruction is in a stage, that is, we call the computation delay. And for some stages, when instruction visit some stages, for instance, the fetch stage or the memory stage, the instruction can make an access memory, and this access can be a hit or a miss, and each of these events are characterized by its respective delay. We have modeled this static architecture in TLA. Here we see that the graph is represented as a subset of the graph is represented as a set of edges, each edge being a couple of stages. And we have relied on the TLA PM library in order to represent the transitive closure of the graph. That is, we say that it is transitively closed. The graph is transitive. And we have also relied on the TLA PM library to say that the order of stages is well-founded. We see here that this is in a comment, since when we make proofs, we can use this assumption. However, if we make model checking, this assumption cannot be verified, since it relies on the non-existence of a function and cannot be model checked. This is why we have a comment here on this assumption. So all the static architecture has been modeled. This is how we have modeled the static architecture. For instance, we have considered two generic sub-architectures. The one that is known as the Han-Rennecke case study. It is an architecture where we have at most one instruction in a stage, and we do not have join nodes. That is, well, we will see this, what it means to be a join node on the figure. And for our that, and we have also considered for the Minotaur project is more complex, and here we can have queues between stages, and we can have also fork and join nodes. To illustrate these aspects, this is the Han-Rennecke architecture, and so here we have the acyclic graph of stages, and here this is what we usually call a join node, that is, it joins between different stages, but this is not a true join node because this is the last node of the pipeline. So this, we consider that in this architecture, we do not have join nodes. In the monitor architecture, it is more complex. We have a fork node, and here we have a join node, and here it is more complex because this is a true join node, because this node is followed by another pipeline node, and then it is necessary to have a specific hardware mechanism to handle this kind of nodes. That is with what we usually call the scoreboard. Now about the dynamic architecture. The dynamic architecture, in fact, is concerned mainly by how the instructions move over the pipeline. We consider that instructions move between stages in a synchronous way. The global move is done according to the node capacity, that is the node full or not, and the readiness is that that means, has the node terminated its computation or not? And the one requirement is that the move over the pipeline should be maximal. That is, if a node is free, and we should not leave an instruction that wants to move to this node. It is mandatory to move an instruction that is ready to a free node. We remark that, well, this is not usual for a TLA plus case study, because usually in TLA plus we consider distributed systems, and distributed systems we have asynchronous concurrency. Here we have synchronous concurrency, that is, the stages compute simultaneously, but in a synchronous way. And this synchronous concurrency is the concurrency we have usually in the synchronous languages, and it is known that it is deterministic. So how we model the dynamic architecture in TLA? So we have first to, since we aim to design a generic architecture, we have only stated what should be the properties of what we call a ready status for instruction. So we have some assumptions about this ready status and about who should leave states. For instance, here we state that if the instructions that are in the pre-state is not empty and there is a ready instruction, then this instruction should be the minimum of the instructions that are in the pre-stage. And we can state this because we have supposed that instructions are totally ordered, so the min is defined because of this order and because the set is not empty. So here we have some well, some assumptions. So for instance, here we have stated in general way that if instruction is ready, then its counter, that is the instruction should have terminated its execution on this node, then its execution counter should be 0. Now we state what is in fact the move of this the move in what is a move, what is a synchronous move. So here we state for all the instructions, if the stage is post, then the instruction has reached the post state. There is nothing to do for this instruction. So it is a stuttering step for this instruction. If the instruction is ready, and here we have the synchronous aspect that is considered, the instruction has to be ready, and its next stage must be free for the next cycle. This is what is expressed by this will be free. And in that case, the instruction advances to the next stage, and it takes now the latency of the next stage. Else, either the instruction has still to compute on the current stage, so it remains on the current stage, or the since the will be free, the test is false, that means that the next stage is not yet available, so the instruction has to stall in the current stage. So here, this instruction, this else expresses that here either we compute or we stall, but we remain on the same stage. The will be free is expressed in a recursive way, because if a stage will be free if either this is the post stage. Recall that the post stage is a virtual stage, or there is not any instruction on this stage, or recursively there is an instruction on this stage that is ready, and its next stage, this is why we need extraction, because we have to say that its next stage will be also free. So we have here a chain of calls to the will be free function, and so the instructions will, thanks to this recursivity, instruction will move according to the status and the readiness of the different nodes in the pipeline. Of course, this definition is recursive. We have to assert its validity, and here we use the hypothesis that we have made in the beginning, that is the set of stages is well founded. So, and last, now we have our transition system. So our transition system, we have the variables here, clock and state. So here, clock is mainly an auxiliary variable to facilitate the reading of traces. But the main thing is that we have the state, the state, the state that is where are the instructions and what is the current execution time. Initially, the clock is 0, and the state says that all the instructions are in the pre-stage. And now the state prime is we compute a cycle on the current state, and we update again the clock just to have a read for trace readability. So here we have our transition system, and we are in the usual TLA but with context. That is, we have the init and next, and we will be able to state the usual TLA properties, safety and liveness properties through this init and the next predicate. Now, in order to state the properties, we will first define what we call state ordering in order to reason about the stages, and we will give some basic properties, in fact, one property. And last, we will discuss about the monotonicity property. First, about the stage, about the state ordering. This state ordering will allow us to reason about the progress order of instructions. An instruction is characterized by its stage and its counter of time, that is its execution time over this stage. So we say that the couple state counter is less or equal than the counter state 2C2. And here we have a kind of a lexicographic order. So we say that either the stages belong to the graph, to the graph of stages that we have supposed that we have a partial order, that or we have equality over the stages, but the counter of C1 is greater than the counter of C2. If, intuitively, this predicate says that this couple stage counter is behind this counter, this coupled state counter. It is behind because either the couple of stages belongs to the graph, to the edges of the graph, or we'll have instructions on the same stage, but the instruction 1 will spend more time in the first in this stage because its counter is greater than the counter of the second instruction. So this is a partial order, and we can reason. We will reason about this progress order thanks to this partial order. Of course, we usually define the less relation in the usual way. So this is an order about instructions. And now we state about the pipeline state progress. So the pipeline state progress is a global predicate about the stage of the pipeline. So we say that the global state of pipeline 1 is less than the global state of pipeline 2, if for each instruction the couple stage counter is less for each instruction in the couple stage counter of this instruction in state 1 is less or equal than the couple state the couple stage counter in state 2 for instruction E. And again, this is a partial order, and we define the strictness relation. I illustrate the use of these definitions now on the one property that we call positive progress. Intuitively, positive progress says that globally the pipeline should not stall. At least one instruction should move over the pipeline. And this property is, and the idea of this property is that, as usual, we have to exhibit one instruction that will always move over the pipeline. And if we suppose that the move on the pipeline is in order, that is an instruction does not overtake a younger instruction over the pipeline, that is, we suppose that this is a property of the pipeline, then the idea is that if we consider the farthest instruction in the pipeline, then this farthest instruction will always move. And since this farthest instruction will always move, the pipeline cannot stall globally. So the idea here is that first define the in pipeline, the instructions that are in the pipeline, that is the instructions that have not yet reached the post stage, then we define the farthest instruction as the minimum of these instructions of the pipeline, and we define the invariant that we will use to prove the positive progress. And this invariant says that either the pipeline is empty, or if we consider the next stage of the farthest instruction, this next stage satisfies the following predicate: either this next stage is post, or there is not any instruction currently on this stage. And thanks to this, what does this mean intuitively? It means that for the farthest instruction, either its next stage is post, then the farthest instruction can move to the post stage, because the post stage is a virtual stage where everyone can move, or there is not any instruction on the next stage of the farthest instruction, and then the farthest instruction can move to its next stage, and again the pipeline is not globally stalled thanks to the move of this farthest instruction. And this is stated formally in this lemma. So if we have this lemma, we have these properties as hypothesis, then we say, well, we have stated it here in this way, that either the next stage of the farthest instruction is and the farthest instruction is post, then there is not any instruction on the next stage of the farthest instruction. And thanks to these properties, we can state formally the positive progress. And as usual, in order to state a property, we had to exhibit invariants that are necessary to have this strict progress property. Last, with respect to monotonicity, in order to the basic idea in monotonicity, we say that if we have in the pipeline, if we have instructions that makes more hit than instructions in another pipeline, then in fact the second pipeline should be more advanced according to the order we have given than the first pipeline. So here we just remark, this is what we call an hyper property, because we do not reason over one execution, but we reason over two executions: the executions over the first pipeline and the execution of the second pipeline, and we want to compare the executions over the two pipelines. So this is why we call this an hyper property. So we in TLA we state this property as follows, and Lamport has already discussed about the expression of this kind of properties in TLA. So we have two instances of the transition system that we have seen previously. We have two instances in order to have two distinct traces, and here the monotonicity is stated as follows: if we have the invariant on state 1 and on state 2 in order to consider only valid traces, if state 2 is less than state 1 according to the global order we have defined on state, then the cycle, what we have called the intuition and the avoiding anomaly, the cycle must not break this fact, that is pipeline 2 is less advanced than pipeline 1, and this order remains after the execution of a cycle. So, of course, the monotonicity is based on a generic invariant. The invariant that we have worked on currently is a mutual exclusion inside the state, the in-order property, and we have also an invariant linked to the ready predicate that we have only specified abstractly. And this is, in fact, under study. For the experimentations, we have considered two basic architectures, as we have already said, the Hahn-Reinecke case study and the Minotaur case study. For the Hahn-Reinecke architecture, we have recalled its features that we have. It is it's simple architecture with respect to the Minotaur architecture. We have at most one instruction on a stage, and you have no join node. We have done a first development in event B, where we were considered mainly by the abstractions and the refinement between these abstractions. And then we have proceeded to Isabelle HOL and TLA plus, mainly for the proofs. To conclude, what I have presented is a generic architecture. It is generic in the sense that we have a general graph and we have general hypotheses about the instructions that execute over this graph. We have mainly considered the mechanization of a case study, a known case study, the so-called Hahn-Reinecke case study. We have expressed its properties, and we have tried to express this case study as an instance of the generic architecture we have proposed. For future work, we want to tackle more deep way the Minotaur case study, and this is more complex because now we will have stages. The stages have FIFOs, that is when instruction leaves a stage, it doesn't go directly to the next stage, but it goes to the next stage through an intermediate FIFO. We have join nodes, and then so we must consider the scoreboard mechanism in hardware. And also in Minotaur, we have some architectural optimizations that we will have to validate. To sum up, we have formalized a generic hardware pipeline environment for experimentation. That is, we are mainly concerned by formalizing the properties and expressing properties about them. We have to formalize the necessary. Sometimes we do not have exactly the necessary assumptions. We have stronger assumptions or sufficient assumptions to prove these properties. And this is where the discussion with hardware people is very interesting, because they are aware of the necessary conditions, and sometimes these necessary conditions are very hard to prove, and this is why sometimes we also consider only sufficient assumptions. And for validations, we want to be able to make validation through model checking or simulation. And of course, as usual, this work relies on the fact that we have to exhibit the generic invariance for the generic architecture we have proposed. Well, thank you for your attention. If you have some questions, it will be my pleasure to answer.
Thanks, Baboon. Questions? Jesse?
You said at the beginning that you were interested in the worst case execution time. What tools did you use for determining that? Because that was not in TLA plus, right?
Yes. The hardware team we work with has its own worst case execution time. It is called Ottawa, and it has it well it is mainly for real-time systems, and it is available, and you can get it over the web, and you can make worst case execution time analysis thanks to this tool.
That's called Opera, OPERA?
No, Ottawa.
Ottawa. Oh, okay.
Ottawa,
Thank you.
like in Canada, Ottawa.
Got it. Got it. Thank you.
But with one, I think it's one T or two T. It's not like Ottawa is written in Canada.
Okay, more questions? Andrew has one.
I saw you were using the Unicode symbols for TLA plus. Do you use them during development, or did you just transform them for this presentation?
No, my code with sorry. In fact, it is only for the presentation. I use VS Code, and I use the basic TLA way to write these symbols, and then it's only the presentation, the listing package of LaTeX that transforms this symbol to Unicode.
Oh, there's also something called the TLA plus Unicode converter. It's a little
Yes,
command
yes,
control.
yes,
Yeah.
yes. I know. It is also in the project to use them. Yes, yes.
You have a question, Finn? Okay. Okay. I have a question, Mamoon. So in your property, it sounds like, intuitively, it sounded to me like a liveness property, what you describe as positive progress. Would that be fair to say?
Well, you can consider the positive progress, you can consider it a liveness progress, but it is very simple because it is a liveness over one step. Usually when you have a liveness property, you have leads to, and the leads to, you have to exhibit a measure in order to show that the leads to, that this measure decreases, and you eventually reach your final state. But here it is very simple because it is just one cycle after that the state, the measure is decreases. So in the spirit, yes, it is a liveness property, but it is I would say that it is a very simple liveness property.
Yeah, and I guess it keeps you out of the realm of temporal formulas, right? So in TLabs, you don't have to reason about the temporal operators, right?
Yes, yes, that's right. This is why we can use in fact, the basic logic to have this property.
Yeah, makes sense. Anybody else? Then I'm not familiar with the what is it, Hein and Reinecke and Minotaur case studies. Can you perhaps in a few sentences say what sort of the underlying motivations of those case studies are? I was thinking in terms of GPUs when I heard pipeline architectures. Would that be
Yes. Well, in fact, these architectures are for real-time systems, and mainly for avionic systems where WCAT is very important for the certification. We have to be able to calculate in a safe way the WCAT for such architectures. And here in fact, these two architectures are, I would say that they are the main representative, today the main representative architectures that have in mind or have in the goal to to avoid anomalies in order to make the the computation of the WCAT tractable. In fact, when you make the assumption that if you have a state less than the other, then when you execute a cycle, you keep this order. This is what allows you to prune the states that you usually deploy for calculating the WCET. And if you don't have this property, you cannot prune the tree of possibilities, and so your calculus remain complex and you cannot manage to calculate it actually. This is why these two architectures are, and this concept is important for architectures where we must have the certification of the WCET.
Okay, thank you.
Thank you.
More questions? Nope, then let's thank our speaker again, Mamoun.
Thank you.